going on to the topics of inferential statistics, we need to get a little bit more of a refresher of our basic probability ideas and rules and theorems so that we can have that foundation when we go to our probability distributions, both of discrete random variables and continuous random variables, and that will help lay the basis for us to do the work with our inferential statistics. So let's get started. Here we're looking at just the idea of probability. Now, probability is the likelihood that a random event will happen. Now, there are three different ways to assign probability. The first one is the empirical method. Now, the empirical method is when you actually perform the experiment, or you collect data, or you simulate an experiment to get information from a real world situation. Now, the next is the classical approach. The classical approach is when you look at theoretical formulas or you look at a sample space to form the ratio that gives you your probability. And then the third way is subjective. Now, subjective method of assigning probability involves some sort of personal judgment of what you've seen in the past. Our idea of then how we would look at each of these and do the assignment of probability with these different methods. What we look at first with the empirical method, here what we would do is one way would be like relative frequency. So we would repeat an experiment and keep track of the number of times that the event we were focusing our attention on actually happened, and also keep track of the number of times that we did the experiment. And then we make a ratio of the number of times the event occurred divided by the number of times we did the experiment, and that will be the assignment of probability. Now, when we talk about the notation also, the notation for the probability of an event is your capital P, and then open a parenthesis, and then put in either the wording of what the event is or the name that you gave that event. And that's equal to your ratio of how you've assigned your probability. So one way with the relative frequency or with the empirical method, let's say we wanted to assign a probability that we saw a heads when we flipped a coin. Now, if I'm doing the empirical method, I want to repeat the experiment and see what happens with it. So I would take a coin and I would flip the coin a specific number of times, and I would keep track of how many times I saw heads out of how many times I flipped the coin. When we're doing the work with the empirical method and the relative frequency, if I just flip the coin, say, once, then either I see a heads, and I would say I saw it once out of one experiment, which would give me a probability of 1, or I wouldn't see a heads, I'd see a tails instead, and then I would have 0 times I saw the event out of 1 time that I did the experiment, and I would have a probability of 0. So when I'm doing relative frequency, I really need to do more of the experiments so that I can get a better value that approximates the probability when I look at using the empirical method. In fact, on the next board, I'm going to write out something called the law of large numbers that tells us that the more often we do the experiment, the larger and larger and larger times that we do the experiment, assigning probability with the empirical method, the closer our empirical method assignment of the probability will be to the actual probability of the event. So here is the law of large numbers written out. As an experiment is repeated over and over, so you're going to do the experiment over and over and over, and you might physically do the experiment or possibly simulate the experiment with some sort of technology. The relative frequency probability of an event tends to approach the actual probability. So I flipped a coin and I kept track of how many times I saw heads and then how many times I flipped the coin. And you can do this too. Your relative frequency probability assignments will be different most generally than what I've gotten here because we are doing the experiment, and so it just from time to time will vary. But the law of large numbers says, as we repeat it over and over, our relative frequency probabilities when we did a large number of the experiments will actually tend to have the same result in our probability assignment as what actually the theoretical probability is. So when I flipped the coin once, I didn't see a head. So my probability of heads, just with one flip, it just came out to be an assignment of 0. Now, when I look at what happened when I flipped the coin 5 times, my probability of heads then turned out to be 2/5. I saw heads twice, and I flipped the coin 5 times. And when we look at just a small number of times that we did the experiment, we see, like, for one flip, I'm either going to get a probability of 0 or a probability of 1, and I know the probability of heads is not 0 when I'm flipping a coin, and the probability of heads when I'm flipping a fair coin is not 1. It's a number in between there, but I didn't do enough flips of the coin. I didn't do enough of the experiment to get a good approximation of the probability with my empirical method when I only flipped it once. Now, when I flipped my coin 3 times, my probability of heads turned out to be, well, the number of times I saw heads divided by the number of times I flipped the coin, so 3/10. And then when I flipped the coin 20 times, my probability of heads came out to be 11/20. And then when I flipped the coin 100 times, my probability of heads came out to be 48/100. Now, we know from the working with probability, if I have a fair coin, if each side of the coin is actually equally likely, then there's one side that's heads out of 2 sides that occur. That's the classical method of assigning this probability. So I know from that classical method that the probability of heads should be 1/2. And as I see, when I got further and further with repeating the experiment over and over and over, I got closer to 1/2 as a probability assignment with my empirical probability than when I had a fewer number of doing the experiment itself. Now, that gives us the empirical approach. The subjective approach is personal judgment, so we don't spend a lot of time on that one. But the classical approach, there is a lot of basis of the way we can assign the probabilities and different formulas that we can use when we have compound probability events, and that's what we'll focus on. So when we're talking about the classical approach, we're talking about finding the probability of event E. So remember to signify that you're finding the probability of event E, or that you're answering the probability of event E. You do a capital P for probability, open parentheses, either write out what the event is or the name that you've associated with that event, and close your parentheses, equals, and then the ratio you find by either your empirical method, which is the number of times event E occurred divided by the number of times you repeated the experiment, or by the classical approach, the number of ways event E can occur divided by the number of possible outcomes. So when we were looking at our flipping our coin just once and looking at the probability of heads, the way that heads can occur is 1 time out of the number of possible things that you could see when you flip a coin is 2, either heads or tails. So our probability of heads is theoretically 1/2. Now, what about other situations that might not be as easy for us to get what's called the sample space? And your sample space is just a listing of what can occur. So here we have, find the probability of a family of 3 children will consist of 2 girls and 1 boy. So I want to think about how all of the distributions of the girls and boys could happen in a family of 3 children, and then look at finding my probability of this with the classical approach. One thing that can help us make a sample space, if it gets a little bit confusing to keep track of what we've already listed and what we still need to list, is something called a tree diagram. With a tree diagram, we're going to do our start with just a dot. So that's the start of listing everything out. And then you branch off that start with the different things that can occur at each stage of creating that sample space. So when I think about the family of 3 children, I think, okay, for the first child, it will either be a boy or a girl. Now, off of each of these branches is where you're going to do the options for the second child. So that second child will either be a boy or a girl, and that will be the options that occurred depending on what they had in your as their first child gender. Now that's your first child's gender, then the second child's gender, and now going to the third child, they'll either be a boy or a girl off of each of these branches. And so you see they call it a tree diagram because it branches off into the different stages of then making the full situation that they've described. And then from the start, I follow the branches to get my sample space. And a sample space is the set of all possible outcomes for that experiment. So for my first branch, it could be boy, 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 or boy, boy, girl, or, so boy, boy, boy took that branch, boy, boy, girl took that branch, so now I'm going to go boy, girl, boy, then boy, girl, girl, then girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. And I wanted to make sure not to go off screen. So normally you would just make that list all the way across, but I wanted to make sure you could see all of these. Now my question is to find the probability. A family of 3 children will consist of 2 girls and a boy. So the probability of 2 girls and 1 boy, and it doesn't specify the placement within the family that it happens, it's just that's the makeup of it. So then I look, and 2 girls and 1 boy would be 2 G's and a B. So here's 2 girls and a boy, here's 2 girls and a boy, and here's 2 girls and a boy. So I have 1, 2, 3 ways that 2 girls and a boy can happen out of 1, 2, 3, 4, 5, 6, 7, 8 entirely possible outcomes of a family, of the gender of the children in a family of 3. And so that gives me that my probability of having 3 children that consists of 2 girls and 1 boy is 3/8. Now when we assign probability, we can either give it as a fraction in simplified form, or as a percent, or as a decimal. If you do give your answer as a decimal, you want to give it in 3 significant digits. I do have a video of how to determine significant digits in a value, and I've posted it in the description of this if you need a review of significant digits. But this is an example of using a tree diagram to get our sample space, and then being able to look at the number of ways event E can occur divided by the number of possible outcomes, using that idea of a sample space with equally likely outcomes. So next up, we'll look at some other information about probability so that we can make sure that we have a good foundation of really looking at our answers and making sure that they have a value that makes sense for what's being asked of us. One is that when you look at the probability of an impossible event, something that can't happen, that probability is 0. So if I were rolling a 6-sided die, that on the faces of the die it said 1, 2, 3, 4, 5, 6, and I wanted the probability that I saw heads when I rolled a 6-sided die, well, I'm not going to see heads when I roll a 6-sided die. So the probability of heads while rolling a 6-sided die is 0. It's an impossible event. Now, the probability of an event that is certain to happen is 1. So if I had where I said, well, what is the probability that I see heads or tails when I flip a coin? Well, I'm either going to see heads or tails. That's certain to occur. And so that probability would be 1. Next, for any event A. So if I'm calling my event A, the probability of A notation is my capital P with open parentheses, A, and then close parentheses. And that probability is always going to be a number that is between and including 0 and 1. So this is really important to remember, especially when we get into probabilities later on, when we're looking at other probability distributions and we're applying our theorems, or we're working with our calculator options to help me find probabilities in my binomial probability distributions or my normal distribution or whatever. And when it reports to me on a calculator, if the number is so small that it's without beyond the readout of the calculator to report it to you, it'll put it automatically in scientific notation. And when it puts it in scientific notation, then it gives you a product of a number between 1 and 10 and a power of 10, which would have a negative exponent on it to put it back into standard notation. If you forget that your probability has to always be between 0 and 1, then when you first read that part of it, you might forget that that doesn't make sense, that my probability comes out to be something like 3.217, and you might just write that down without looking at the whole number, seeing that it says 3.217e negative 4, in which case that means 2.317 times 10 to the negative 4 power, so that really is 0.000317 for the probability instead of just that first part. So I know I'm talking about this a little bit ahead of the game, but I just want you to always remember that your probability has to be between 0 and 1. So if you get a number back on your calculator for probability that's not a number between 0 and 1, it's very, very possible that it's reporting it to you in scientific notation. You just have to make sure you read the entire thing out to put it back into standard notation. Now, I also have a video on scientific notation, and I'll include that link in the description of this one as well, just in case you needed to review that too. Also, with probability and with our sample space, the complement of an event is something sometimes is easier to calculate than the probability of the event itself. And if I calculate the complement of the event, I can find the probability of the event itself through a relationship of the probability of a complement and the event. So right now we need the notation and the idea of a complement of an event. The complement of an event A is denoted A with a bar over it. So that's A complement. Now this brings something that I need to also forewarn you about. In mathematics, just like in English, just like in a lot of different settings, there are times where words or where symbols that look exactly alike mean something entirely different than each other, and you have to tell what meaning it has by what context it is being used in. So, case in point, if I have X with a bar over it and I'm working with a data set, that is the notation for sample mean. But if I'm working with probability and I have a name of an event with a bar over it, that means the complement of that event. I have to take it in context, and I have to really have a solid foundation of the symbols and what they mean so I can interpret what I'm asked to do correctly. Also, the letter P is going to be used in a lot of different settings in statistics. Capital P with the name of an event over it is asking you to calculate a probability. Small case p later on could represent the probability of success within a trial. It also can be abbreviated that way on your calculator screen to represent the p-value, which has a meaning of the probability of being to the extreme of the test statistic. So there's a lot of different places that the letter P is used in statistics. Also, the population proportion is designated with a small case p. So again, context is key. You have to make sure you really look at the context in which the symbols are being used to appropriately get in the information they're trying to portray to you. So our denoted A complement, and it consists of all the outcomes in the sample space that are not in A. So when you have your whole sample space, you look for a complement by saying, well, what is the set that makes up the event A? Then everything left over in the sample space from after those are kind of taken out, that's your A complement. Now let's look at some other properties of probabilities. The sum of the properties of all outcomes of a sample space must equal 1. So if I have a sample space, A is equal to the events, A sub 1, A sub 2, A sub 3, up to A sub n. So here we're using capital A for the name of the sample space of the event, and then the elements within the sample space are small case, that letter, with subscripts. Now if I take the probability of the first event in the sample space plus the probability of the second event in the sample space plus the probability of the third event in the sample space all the way up to the probability of the nth event of the sample space, that has to be 1. I can also symbolize this addition of the probabilities of the events by capital sigma. That means to add up the probability of the events, and that's getting incremented from 1 up to n. So I just put a little index of summation there, sub I, and then say my I goes from a subscript of 1 up to a subscript of n. So that's what that symbolism means, and if I add those all up, I get 1. Now, an unusual event is an event with a very low probability. Now, usually we say an unusual event is one that has a probability smaller than 5%, but there are certain situations where the percent that it's less than, usually we say that the probability of an unusual event is something that has a probability that's less than 5% or less than 0.05 in decimal form. But that's not like a definition cutoff that they give. Certain situations set their own cutoff of an unusual event. For us, a lot of times if it asks you if the event is unusual, as long as its probability is less than 0.05 or smaller, you can say it looks like it's an unusual event. And then complements. Because our probability of our events in our sample space has to total 1, and when I talked about the definition of a complement of an event, so the complement of event A is all of the other things in the sample space that's not in A. That means between the two of them, they make up the entire sample space without any overlap. So if I add the probability of event A occurring plus the probability of the complement of event A occurring, that has to total your 1 that we've gotten up here. And once I know that, I can rearrange this equation to where I might be able to use it in another setting. So if I want to find the probability of event A, but it's really hard to get at, but the probability of its complement is really easy to get at, then I can find the probability of event A by taking the value 1 and subtracting from it the probability of A complement. Now, one other thing I want to say without writing it out, but that you probably want to just take note of, the complement of at least one is none. So even if we look at our situation with families, the gender of children, our situation where we look at the gender of the children in a 3-children family, well, if I look at wanting to know the probability of at least one girl, I could go back to my tree and count them out. But the complement of a family having at least one girl is having no girls. And the probability of a 3-children family having all boys is 1 out of 8. So I can find my probability of at least one girl by taking 1, subtract the probability of no girls. So that's 1 subtract 1/8, or 7/8. So that's where this situation with knowing our idea of our complements and this relationship between the probability of an event and the probability of its complement adding up to 1 can help us in a lot of different settings. We also will often come across things called compound probabilities. With a compound probability, there are different situations that can involve more than just a simple event. One of the first compound probabilities that we're going to look at is for our probability of one event or another event. So when we're looking at the probability of A or B occurring, then I need to first ask myself, are there any elements that have both of the characteristics that A as well as B are describing? If there's nothing in my sample space that would have the characteristics that are both A as well as B, then they're called mutually exclusive. And if the events are mutually exclusive, to find the probability of A or B, you find it by taking the probability of event A, adding to it the probability of event B. So when it's or for your compound probability, you add the probabilities. Now, if the two events are not mutually exclusive, if there are elements that have both of the characteristics, then you're going to overcount them. When you do the probability of A, you'll count them in there. When you're looking at the probability of B, you will have also counted them in there, so you've overcounted. And you need to subtract off the probability of the likelihood, the probability of event A and B occurring. So let's look at some examples. So let's say you randomly are going to pick a card from a standard deck of 52 cards. Now I know, cards are one of those things where some people will play cards a lot, they really understand the deck of cards, and other people just don't play cards, so they're not familiar with them. The problem with not using decks of cards in examples and describing things is that if you come across something that asks you about them, then you still haven't had that opportunity to become familiar with them. So also another thing is that the characteristics of a deck of cards play out so well for different types of compound probabilities, they're really hard to stay away from. So just a little review of a deck of cards. There are 52 cards in a deck, a standard deck. It's broken up into 4 suits: the hearts, the diamonds, the clubs, and the spades. Each of those suits have the same number of cards, so 52 divided by 4 is 13. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. In the suit, the cards go from ace, which is kind of your 1, so ace, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, and then after that it goes jack, queen, king. That's how you get your 13 cards in this suit. Now the jack, the queen, and the king are all cards that are people cards, so they have faces, so they're actually called face cards. So there's a jack, a queen, and a king for each of the 4 suits So that gives me 3 times 4, or 12 face cards. So I have 13 in a suit. I have 4 suits in the deck, and we have 12 face cards. And for each of the other members, you have 4 aces, 4 2s, 4 3s, 4 4s, etc., because you have 1 of each suit. So a 2 of hearts, a 2 of diamonds, a 2 of spades, a 2 of clubs. And if you Google it, you can actually see where they'll show you out a deck of cards. Now with that, let's look at these probabilities. Find the probability that your card is a 2 or a jack. So it's or, so I know I'm going to add my probabilities. I just have to decide whether these events are mutually exclusive or not. Well, a 2 or a jack, there's no card that has both the 2 as well as a jack on it, so they are mutually exclusive. So I will take the probability of getting a 2 and add to it the probability of seeing a jack. Well, there are 4 cards in the deck that are 2s. So that's 4 over 52. Plus there are 4 jacks in the deck that are, so that's 4 out of 52. So I have 4 out of 52 plus 4 out of 52, which gives me 8 out of 52. And when I simplify 8 out of 52, I get 2/13. Now, how about a heart or a face card? Well, there are face cards in the hearts. There's the Jack of Hearts, there's the Queen of Hearts, and there's the King of Hearts. So I do have it where they're not mutually exclusive. So to find my probability, I'm going to take the probability of heart plus the probability of face card, but I'm going to have to subtract off the probability of heart and face card. And so probability of hearts, there's 13 hearts in the deck. So that's 13 out of 52 plus face cards, there's 12 face cards in the deck. So that's 12 out of 52. And I need to subtract from that the hearts that are face cards. So that's the Jack of Hearts, Queen of Hearts, King of Hearts. So that's 3 out of 52. So when we look at that, we get 22 out of 52. Or 11 out of 26. So those are compound events asking for the probability of events A or B. For the next type of compound events, we're going to look at what if they're asking us for the probability of A and B. So remember, the last one we did was the probability of A or B. And with or, you added the probabilities. And then if you had the events not being mutually exclusive, you had to subtract off the probability of A and B. Well here, what if we're asked to find our probability of A and B directly? And the A and B are independent. Well, independent event means that the occurrence of one event does not affect the probability of the second event occurring. So when I look at whether they are independent or not, I want to think of that second event's probability, and then I want to think about going through what's described to see what the second event's probability would be if event A occurred to start with. If those are different numbers, they're not independent. But if those are the same number, they are independent. So the probability of A and B, if the A and B are independent events, you multiply the probabilities. The probability of A gets multiplied to the probability of B. So let's say I was going to roll a die and toss a coin, and I was looking at what's the probability of a 2 on my die and heads on my coin. Well, what I get on the die is not going to affect what happens when I flip the coin. So my probability of 2 and heads would be the probability of 2 on a 6-sided die is 1 face is a 2 out of the 6 faces of the die. And I multiply that by the probability of heads when I flip a coin is 1 side of the coin is a heads out of 2 sides of the coin. And when I multiply, you multiply straight across the top, straight across the bottom. So that's going to give me 1 times 1 is 1 over 6 times 2 is 12. So that would be a probability of 1/12. Now what if A and B are not independent? In fact, they're dependent events. Well, if that's true, then to find the probability of A and B, you're going to take the probability of A and you're multiplying it by the probability of B given that A did occur. Because you want the overall probability. So the whole thing has to be fulfilled. So it has to be the probability of B given that A occurred. So with this, if you're looking at what's the probability that when you pick 2 cards in succession out of a deck of 52 cards, you keep the first card out of the deck. So this is without replacing. I'm not putting it back. So then what's the probability of a heart on the first draw? I'm going to put without replacement. But I'm not going to put it back. Heart on the first draw and a heart on the second draw. Well, if I keep that card out, then the probability of the second thing is going to be affected by the first card being held out of the deck. So a heart on the first draw, remember there's 13 hearts out of the deck of 52 cards, so 13 out of 52 times, and now I want the probability of getting a heart on the second, given I got a heart on the first, because I have to meet the full requirement. So that card that's sitting out on the table that's not in the deck anymore is a heart. So now I only have 12 hearts out of only 51 cards that I'm pulling from. And then when we work through simplifying this, multiplying it straight across the top and straight across the bottom, but to keep the numbers a little bit more reasonable to work with, you can remove common factor pairs. So 13 goes into 52 4 times, and 4 goes into 12 3 times, and that gives me, and 3 actually can be simplified as a common factor of 3 and into 51. So it's 1 in the numerator and 17 in the denominator. So I have this probability being 1/17. So that's what we have when we don't have independent events. And then lastly, something called the conditional probability. And the reason I wanted to finish off with this is that it really is just a rearrangement of my compound probability A and B with my events being dependent. So the probability of B given A, given you have extra information about it, just divide both sides by the probability of A. So I get the probability of B given A is the probability of A and B divided by the probability of what's given. That's how you want to think about it when the lettering might be different than this. It's the probability in this denominator is what follows the word given. Now, before we finish up, I want to also mention that sometimes the formulas are really good to use because we have the information in like pieces. Other times they've organized on a table format are like information that we've gathered like in data, and I'm doing a probability by like empirical assignment. So I won't always use these formulas. If the organization structure of a table makes it easier for me to read directly from the table, then we will get those probability assignments that way. And I also have a video on finding probabilities from a table, and I've linked that in this description as well. Well, hopefully this gives you a start of some solid notes about the background, about just the basics of probability, and and we'll go on from here to get into probability distributions and then work with that in a foundation that we'll need in our inferential statistics.